Back today talking about the entropy of mixing for basically Bragg-Williams theory. So again, this is just kind of a starting point before we get into polymers, which again, as we know, polymers are the most difficult material to study. If you could study polymers, you could study ceramics, metals, everything else very, very, very easily. We're going to start off by basically looking at how Bragg-Williams, they've kind of applied this theory of kind of the entropy and the full free energy of mixing. So we're going to try to develop again, this delta G of mix. Just going to compose the delta H, some enthalpy contribution of mixing, minus T delta S of mixing. So Bragg-Williams, they've done this, and we're going to go through this derivation for small molecules. So small molecule mixing, so chemical mixing, or even gases. So before we get into polymers, that's what we're going to kind of deal with. So we are going to have, basically, this is our situation, our schematic. We have some initial state here where we're completely unmixed. Then we're going to transition to some final state here where we're mixed. So in this system, you can kind of think of it as like a lattice, so a grid. So in our lattice, we have a total number of n naught lattice positions. So that's our total number equals total number of lattice positions. And we have N1 molecules, we'll call those our red molecules, and we have N2 molecules, which we'll say are our blue molecules, where, again, we fully occupy every side in our lattice, so N naught equals N1 plus N2. So that's kind of the situation that we have here. So we need to kind of look at and calculate what is going to be the entropy of mixing. So we know, and actually we'll go on to the next page here. We know, and then this is kind of, again, just what we've kind of said previously, N naught will fit all points of the lattice, exactly. So we know the number of ways you can arrange species 1, species 2 on a lattice of N naught points, where, again, N naught equals N1 plus N2 is just going to be our binomial, again, these different number of configurations, all those permutations. It's just going to be N naught factorial over N1, N2. Again, this is very similar, like we talked about previously, for our random walk. So we remember back, so our random walk of n steps equals n plus minus n plus n minus steps. That's kind of what we were dealing with previously here. So very similar idea, same again, similar distribution that we saw. Number of microstates or configurations is just going to be factorial over minus factorial right there. So this gamma 1, 2 is the number of configurations for our, basically, we're going to call this our mixed state. So when we look at this presentation here, so this is, we want to look at the number of configurations in the 1, 1, because this is our N1 molecules, these are N2 molecules, this is going to be our gamma 2, 2, and then when we have our fully mixed state, we're going to call this gamma 1, 2. So before we head back into the next one, what is the number of ways, if I'm in this initial state, what are the number of configurations in my 1, 1? And what are the number of configurations in my 2, 2? Well, if my initial state is all the red molecules are isolated, all the blue molecules are isolated, the number of configurations is just 1 for these two. And we just saw previously how we could calculate the number of configurations for our mixed state, which is this right here. And we know from our Boltzmann expression, we could relate the entropy, the configurational entropy, the configurational entropy, and again, not the conformation. So again, this is a little bit distinct, but similar to your conformational entropy of your polymer. But we know we could relate entropy to the number of configurations, and it's just related to this equation. So we know what is log of 1? That's going to be 0. So when we look at our delta S of mixing, the change in entropy from going from this initial state to this final state, the delta S in mixing, the change in entropy upon mixing is just going to be S12, entropy in the mixed state, minus your entropy in your initial states. But we know that this is 1, so that's going to be 0, 0. So our delta S of mixing is just this function. So we'll do some math and some rearrangements. So we'll use Stirling's approximation, and we'll use this expression of phi1 is equal to, and a lot of times I'm just going to write it as just like I'm not going to write it like this, I'll just write it as phi, but I'll try to be a little bit more consistent. So phi1 is equal to n1 divided by n naught. This is, for small molecules, this is both the mole fraction and the volume fraction of our species. We're going to see for polymers that these are not necessarily, this will not always hold true. Specifically, for polymers, the mole fraction and volume fractions will typically be not equivalent. So Phi1 and Phi2, for Bragg-Williams, they're equivalent for mole fraction and volume fraction. But moving forward, we're going to say that Phi1 and Phi2 are the volume fraction of each species. But anyways, we'll hit on that a little bit later. And Phi2 is equal to N2 divided by N naught. And we know that, again, from our definition here, that N naught equals 1 plus N2. So we know that Phi1 plus Phi2 must equal 1. And again, both of these values, they can only vary from 0 to 1. So rewrite this expression. You could do the Stirling's approximation. I am not going to go through that here. You could use Mathematica or kind of derive it yourself. And if you have any questions, we could discuss in office hours. But you get this expression right here. And so this is the Bragg-Williams change in entropy for small molecules. And if we want to get a molar quantity, we have to kind of divide out by the number. Molar quantities, again, are very beneficial to use because, again, it's just we've kind of divided out by the number of moles. Molar quantities are nice to work with. So if you divide out, and you'll see that in literature a lot, if we divide out by the total number of lattice, sites and particles, you'll get this expression right here. So we have our delta S of mixing as a molar quantity. Sometimes you'll see molar quantities written like this. So delta S mix. If you see this bar on the top, usually that means like a molar quantity. But anyways, we'll see and define that later. We could also rewrite this expression as using this equation just to write it in terms of one variable. Delta S mix divided by N naught equals K minus P1 log 1. Again, unfortunately, I'm not going to usually do that. And then minus 1 minus P1 and log of minus P1. Just writing it all in terms of basically Phi1s. You'll see why I'm doing that in a second. So this is a very, very, very interesting equation. And we could plot this in Mathematica like so. So when we plot this, actually I rewrote it as Phi2, but again, doesn't matter. Phi1, Phi2, actually we'll go ahead and rewrite it usually in terms of Phi2. We'll see why that is in a second. But if I plot this function, you see something very, very interesting. Can I ever have a delta S of mixing? Again, my Phi2 can only vary from 0 to 1. Can I ever get a delta S of mixing that's negative? No. If you calculate this out, if you go through this expression, it is ever negative. It is never negative. So again, that's going back to the base, the start of this lecture. We said that the driving force for mixing is always going to be entropic. So for small molecules, mixing will you will always gain entropy. Entropy will always increase when you mix. So you always increase your configurational entropy when you mix. So that will always be the driving force for mixing. So that will always lead or push towards mixing. And then we have to see, can we overcome the energy barrier, the energy penalty associated with that enthalpic cost? So there's also lots of kind of cool things in here. When is my entropy maximized? Well, I could, if I want to kind of prove that, mathematically, I just flip my thing here. Okay, here. So what value of phi is this maximized? So let's take my expression, Bragg-Williams entropy. I'm going to do my Bragg-Williams entropy. I'm going to take the derivative with respect to phi2. And I'm going to set it equal to 0. I'm going to solve for phi2. 0.5. Kind of makes sense, right? Just kind of intuitively. What's the highest number of configurations? When is my entropy maximized? When I have equal number of basically red and blue, marbles or particles. If my phi1 is 0.9, that means my phi2 is 0.1. There's so many. Let's see how I defined it. So many red particles and not many blue particles. There's not going to be as many configurations as when my entropy. So again, you kind of see this nice symmetric relationship as a function of phi2 for your basically your change in entropy upon mixing. So excellent. So as you can see, when is entropy maximized? We see there. And again, that kind of note I mentioned, polymers, mole fraction, volume fractions will not be equivalent. So usually we're going to kind of talk about P1, P2 being the volume fraction of each species. So that is it. That's the entropy of mixing for Bragg-Williams. Next time we're going to get into enthalpy, and then you'll have the full free energy for Bragg-Williams. We'll be able to kind of see what conditions we'll mix, what conditions we won't mix, and then we'll move on to polymers and phase diagrams and lots of fun things coming up, and chi parameters. So that's going to be nice. So I will see you all next time. Thanks.